Hey guys, welcome to 2.4 example 7. We're looking at a fourth degree polynomial here that we have to get the real zeros for. And of the real zeros, we're going to have to find the rational ones first. We're going to use technology, but we're approaching this problem as if we didn't have technology. All right. We're going to use the technology specifically to fast track some of the more tedious work, but we will be focusing on the concepts as we're going. All right. So fourth degree polynomial, here it is. And notice we do have four roots. And of those four roots, two are rational, negative half and 4. Now, if we didn't have the technology, what we would do is look at the first and the last number and know that those are indicative of the rational zeros. So we're going to list out all the possible factors of 8 and all the possible factors of 2, because if we were able to factor this and solve it by hand, the first and the last numbers of a standard form polynomial is going to basically help us get those. Now, with that said, you can have 1 over 1, 2 over 1, 4 over 1, 8 over 1, and 1 over 2, 2 over 2, 4 over 2, and so forth. These are the unique ones that we have. Okay, these are the possible rational roots. But again, we already use technology. If we didn't, we'd have to take the 4 or the 1 or the 2. We'd take all of them, plug them in, or do synthetic division to see which ones get us a remainder of 0 or which ones will get us a 0 when we plug it in with remainder theorem. I've already found, again, pretend that we did that all, but at the end of the day, we know f of 4 is 0. We'll start with that. That means x minus 4 is a factor of f of x. And if it is a factor of f of x, that means that this can divide into that, right? And so we'll do synthetic division, right? I have an x equals 4 for our synthetic division. And we're going from a fourth degree divided by an x minus 4 linear first degree, and our quotient will be a third degree polynomial. Now, we want to make sure we understand that the original function is still this, right? We're finding zeros for this. So even though this is 1 degree lower, this is a part, this is a factor of that, right? So we want to make sure we understand that a function, if we're doing division, long division or synthetic division, it's equal to the divisor times the quotient plus the remainder. In this case, the remainder is 0. So our function is the x minus 4 times the quotient, the 2x to the third, so forth. All right. Now, to reinforce that concept, if I go over here, here's my quotient. Notice it is a third degree, and we've lost that x equals 4 factor. Well, that makes a lot of sense because we divided it out, right? So the original function is this, the fourth degree with 4 roots, and we've separated the x minus 4. So x minus 4 is here, and the cubic is over here. And so notice the cubic contains just the 3 roots. It lost the x minus 4 root. Now, if I want to show you getting it back, I could just make a random function and make it equal to q of x times x minus 4. And notice that is the original function, right? If I take this and times it by x minus 4, it basically becomes the original, right? See, notice that's what it is. So keep that in mind. When you're dividing out a factor of x minus 4, keep in mind that these put together are still the original. If you multiply this back together, it's that. It's like saying, 8 divided by 2 is 4, right? Like, then that means 2 times 4 is 8. That's what's happening over here, all right? Okay. Now, I'm going to show this step. Right over here, this is where, again, you can't factor that by hand easily. So we have to do synthetic division, list out all the possible rational roots. And this time, again, I could plug all of these in or do synthetic division with just this part and look for a 0 or a remainder of 0. With that said, I can see over here that negative half is a root. So I can go ahead, do synthetic division. We're going from a third degree, dividing it by a first degree, and we'll have a second degree. And again, this times this is equal to this. So that means I'm taking this and factoring it into two parts, right? And so now I break it apart fully into even more factored. I can see a GCF there, so I can factor out a 2. And then this is a difference of perfect squares, right? Although 2 is not a perfect square, if you're asked to reduce and factor to irreducible terms, then you can go ahead and say, well, what times itself is 2? It's root 2. Or you can solve it over here on the side and realize that, hey, if you add 2, square root it, you get plus or minus root 2 as your roots, you go put it back in as factors. That works fine too. And here are all your factors. And sorry, all your roots, okay, all your zeros. And notice this, you would not be able to use the rational roots theorem. You'd have to get it down to a point where you can factor by hand. And that's over here. One other thing I could show you is also that if I take f of x, right, and divide it by x minus 4, notice I also get that. So keep in mind that the graphical parts, if you're going from a third degree to a second degree, you end up losing a 0, okay? And that changes how many times it intersects. But remember, the whole idea is that you are maintaining the original function. So even though you're dividing it out, yes, you're dividing it out, but at the end of the day, our goal is to actually maintain all the quotients because they are factors. Okay, so if something is divisible and you factor it out, you're actually factoring it to get all the zeros. Okay, if you guys have any questions, let me know.